Hello and welcome back to the channel. On this occasion I am going to try to give you the information you require for the study of geometric isomerism in different types of compounds, but first we are going to start with a fine-tuning of what we have seen. Isomerism previously. We have here a basic representation of the types of isomers that we have studied this year and within isomerism, and let us remember that isomerism studies all those compounds that have the same molecular formula, that is, the same number of atoms in their molecule. They present different types of properties. At least they differ in one or so within those A types of isomers. We saw that there is planar or structure isomerism, and that planar or structure isomerism is the one that allows me to see the differences when I represent them in the notebook. So within the plane isomerism I have the chain isomerism, the position isomerism, and the function compensation isomerism. For these three types of isomerism, there are other videos on the channel that you can turn to if you still have doubts in the case of spatial isomerism or spatial stereo. There are two types: geometric isomerism, which is what we are going to discuss in today's video, and optical isomerism, which will be in the next video. These two types of isomerism cannot be easily visualized just by representing the compound in the notebook on a sheet on a blackboard. We need to recognize some other things and think about spatial models as we did in class to be able to differentiate them from each other. Let's start today then with geometric isomerism, which was what I told you at the beginning. We know that geometric isomers are compounds that have the same molecular formula but have different structures, and therefore they will have different properties. In order for geometric isomers to exist, they must present a double bond, for example, or be in a cycle. In this case we are going to focus on the geometric isomers when they have a double bond, that is, it does not have free rotation. Why? Because the double bond prevents the two carbon atoms from rotating. They have an impediment, that is the double bond, through which they will not be able to rotate, and therefore once these double bonds are formed, the substituents of the bonds to which they are attached will not have the possibility of rotation. That is what we mean by the fact that the geometric isomers should not present free rotation. I have already previously drawn some structures to be able to work more quickly before going to other types of geometric isomers. Let's remember that I am representing the double bond between two carbons and the substituents with an angle towards the sides and not horizontally, because the sp2 hybridization, the formation of the bond double A, generates in the part of the double bond a flat structure, and in which all the angles are 120 gr. So that is more or less why we put this position of the substituents E, and that is why we do not put it like this. For example, make the difference clarified. This lets A continue with A. What we were talking about, I'm going to delete what I just put, and we continue well A when I do have geometric isomers in a compound when, for example, the two carbons that are linked to the first of those two carbons, the one that is joined, has a substituent that we call and the second also has a substituent that we call A, but the other two substituents are going to be different. They are going to be B and B equal to each other. So in this case, if there is geometric isomers, an example of them and then let's work is the one I'm writing now when the two equal atoms are chlorines and the other two equal atoms are hydrogens, which is the compound 1,2-dichlorine ANO, and then we're going to take care of this one to see how it classified its isomers. Other type of compounds that present geometric isomerism are those that have two identical substituents and the other two can be different from each other to A, B and C, and here we could have a simple example where I have bromine methyl hydrogen, and this compound is 1,2-di. Bromine. Propene. Let's remember that in this case my carbon 1 is this 1,2,3 in 1, and in 2 I have two bromines, and in 1 the double bond. We could ignore the 1 of propene, but that way it would be complete, and I'm going to show you now when I don't have our geometric isomers. For example, if here I have A and A and here B and B, there is no possibility of having geometric isomers. For example, our chlorine hydrogen hydrogen, and this would be 11-dibromoethene, and I just thought of another one to show you what it could be. I have the two atoms of carbons linked together, the double bonds, and here I have, for example, AA to B and an example of this, and I am trying to use simple examples so that you understand it. It could be the one that has chlorine hydrogen, and this is called 1,2-trichloroethene. These last four, let's say, they are the ones that do not have geometric isomerism, so we can say that this one does have geometric isomerism. S has geometric isomerism. It does not have geometric isomerism. It does not have geometric isomerism. We are going to work with one of these examples, and I am going to use the first one. The same example is the one that I am going to use now. I have the compound that we have been working with, 1,2-dichloro A. How can we visualize if this compound has geometric isomers? We are going to focus on the double bond, and we are going to think that the substituents of the double bond, they can be connected like this as we have them represented, or these connected in reverse. Then I would have two carbons joined together by a double bond. There are four substituents. Chlorine hydrogen. Let's suppose but that when this compound was formed, the second chlorine was left in this position, and here I have a hydrogen. This is still called 1,2-di chloroethene because we still have two chlorines with a double bond and two carbons with a double bond, and there I have the ethene, and I have in position 1 and position 2 two chlorines, so it is still 1,2-dichloroethene. But if we think about how the chlorines are united, the chlorine here, it is on the same side as this one, and in the other case this chlorine and this chlorine are in opposite positions to the substituents that their isomers that the same substituents are on the same side, called cis-isomers, and therefore the name is cis-1,2-dichloroethene, and the substituents that are chlorines, in this case the same substituents, are on opposite sides to the compounds that the substituents are on opposite sides are called trans. So this is the isomer trans 1,2-dichloroethene. I am going to use one more example to make this as clear as possible, and I am going to use the compound 1,2-dibromine. Mitre ethene. I am going to draw it has two carbons joined together by a double bond. In the carbon 1 has a bromine and a nitro NO2, and in the second carbon it has another bromine and a hydrogen. We are going to represent it in a more dimensioned way to be able to classify them. So I have to draw the two carbons, draw their 4 bonds, and replace each one with one of the substituents. This would be 1, and the other isomer is the one in which, for example, we are going to change here the first carbon was joined differently. The position of the nitro, the NO2, is different. So returning to the name bromine, bromine, on the same side, bromine, bromine from different sides, so the first one is the cis isomer and is called cis 1,2 diomo 1 nitro ethene, and that would be the full name of the first, and the second is called trans 1,2-dibromo. Nitro A. We are going to do one more example with a compound that we saw previously, which is 1,1,2 trichloroethene. We are not going to use the 1,2-dibromo propene, so let's formulate. I'm going to copy it from here. We are going to use this one that we already had initially, which is the 2-dibromo prop. This one represents the bromines on the same side, so this is my cis isomer, and before the name I put the word cis and the other possibility that I have for the 1,2-dibromo propene is in which the bromine is located in a transposed form on opposite sides. And here I have the trans isomer, then this is trans 1,2 dibromo proper, and this would be all in terms of geometric isomers, also called Cis-Trans isomers. The following video will be made based on the geometric isomers.